Second video on solving quadratic equations, in which we're going to explore how we can do this using what we call the square root property. And so next to factoring, solving by factoring, this is probably one of the easier methods for solving a quadratic equation. And basically we would say that any quadratic equation of the form u squared equals d, if you had just some squared quantity equal to a number, basically we could take the square root of both sides and it would be really easy to solve for whatever this expression u is here. So we say u is an algebraic expression and d is some non-zero real number. We can solve this using the square root property. And so let's go ahead and visit this right now. As a matter of fact, we say the square root property, if u is an algebraic expression, I mean it could be any expression here, we say d is some non-zero real number, then if u squared equals d, then we have exactly two solutions, and they are simply these. We would take the square root of both sides of this equation. We just say square root, and what we would get is this. We get u equals positive the square root of d, and u equals negative the square root of d. Recall that when you take the square root of a number, you get two solutions. It could either be positive or negative, kind of like the square root of 4. It could be a positive or a negative 2, essentially. So using this property, we could say that the square root of both sides here yields two solutions, and they're always just kind of opposites of each other. We're going to see more generally that they're conjugates of one another. So using that property, what I want to do is actually just take a look at these three equations you see here, and what makes these a little bit different than the last video is that you'll notice that none of these expressions here, when you look at this ax squared, the standard form here of a quadratic, plus bx plus c, none of these are going to have this bx term here, which means all we have is just an x squared, or at least an algebraic expression in x squared, which we can get by itself and then take the square root of both sides. So as we look at letter A here, we say 3x squared minus 21 equals 0. Since I don't have an x of the first term, the first thing I'm going to do is I'm just going to add 21 to both sides. And what I end up with is this. I say 3 of these x squared things comes out to be positive 21 constants, followed by dividing by 3. The idea is that we want to isolate the squared thing, the squared expression, which in this case is just the x. So we say 21 thirds is the same as 7. So I would say, well, what would I get for an answer here? Well, taking the square root of both sides, I get a lot of people that just write this on their paper. They say, well, the answer is the square root of 7, which, that's one of the answers, but you have to keep in mind that we would get a positive or a negative result when we take the square root of a number, or fourth root, or sixth root, or eighth root. So we get two solutions here, and as a matter of fact, we do want to write them in set notation. So I'm going to write positive, negative, square root of 7, or you could just write them individually, okay? So these are the solutions to this equation here. And it would be very easy to check that out just by plugging it back in. We'd say 3x squared minus 21 equals 0. Check this out. If I put in a positive or a negative root 7, the fact is when you square this positive or negative thing, you're going to get a positive thing. And the square root of 7 squared is just, well, 7. So we have 3 7s minus 21 is 0. Well, it is indeed the case that 21 minus 21 does come out to be 0. So let's take a look at these next two examples. Notably B. B looks a lot like letter A. As a matter of fact, I don't have an x to the first term, so that means we can just get this squared thing by itself. So I'm going to start by booting the constant term over to the other side, our c term there. So I have ax squared equals this negative c here, in this case negative 45. And I will proceed by dividing both sides by a positive 5 here. So what do you know about 45 divided by 5? Well, we get 9, but in this case, look, we get negative 9, which it doesn't actually ruin my day. I'm still going to take the square root of both sides using this square root property. But what I want to keep in mind is this. I actually get the square root of negative 9, which becomes plus or minus, now here's the important part, I times the square root of a positive 9, which means we're getting non-real results here. Also, I know the square root of 9 can be reduced, simplified, to a 3. So we would say, well, plus or minus, I'm going to let the 3 precede the I. So we say plus or minus 3i are the solutions to this equation here. And again, we can plug that back in and check to see that those are indeed the solutions. So for this last one here, it's a little bit different than the first two. What I want you to understand is when we refer to u up here as being some algebraic expression, I want you to understand that if we said let u really be representative of the quantity x plus 5, then this statement right here could be rewritten as, well, x plus 5 squared is really u squared equals 11, and I can take the square root of both sides and get a result. So because I have just a squared thing here and no x's to the first power, I am still allowed to take the square root of both quantities here. And so we get the square root of x plus 5 squared. Well, that's just x plus 5 as we would naturally get when taking the square root of something squared as the natural radicand on the inside. And then also this, we say, well, the square root of 11, remember we took the square root of this, we did it, so we got to put a plus or minus here. And so the last step and the final step in this particular instance is to subtract 5 from both sides. So keep in mind, negative 5 here, this is not like terms, not like radicals with our plus or minus root 11. But we would just say these are the two solutions right here. So that is how we could use the square root property to solve an equation that has some squared expression in x. One thing I want to do though before we tune out this video is start to take in mind a graphical approach to this. So let's go ahead and take a look at this original equation that I started with over here on letter A. It was 3x squared minus 21 equals 0. And one thing I want to keep in mind is this, well, what if we were saying that our equation really was y equals 3x squared minus 21? It's this thing right here. Really what we're saying is, by setting this equal to 0, we're really saying, well, for then this graph here, which is a parabola, and you can see that this parabola is graphed over here on the right, we're saying, what are the x values that would cause our y values to be 0? And what is significant about that is that if you look at this graph right here, we are looking for these two x values where our y values actually came out to be 0. And so in this case, we get negative square root of 7 comma 0 and positive square root of 7 comma 0. So by setting y equal to 0 and solving for x, really what we're saying is when we're solving a quadratic equation, let's write this down. We say solutions to a quadratic equation are its zeros, quadratic equation, are its zeros or x-intercepts. We're just looking for those. So this will be important as we move forward through these videos, because one thing I can tell you is, I actually put these three equations here. You can see them in my calculator here. We've got our 3x squared minus 21. I've got my 5x squared plus 45 in my calculator, and I've got my x plus 5 squared. And you'll notice that I subtracted 11 from this. I had to set it equal to 0 first before I put this equation in. If I go back and graph this now, I'm going to go in and highlight this graph here. You'll see the same graph that we obtained here, but we're saying that the x-intercepts are positive and negative square root of 7. And one thing is of note here, I did change my window. You can see my window here is negative 10 to 10 by 1s on our x-axis, and negative 30 to 70 going by 10s on my y-axis. So I'm not going by 1s everywhere, but you can see that I did indeed get two real solutions. And if you look really closely here, it's a square root of 7, okay? It's less than the square root of 9, which means it's less than 3. You can see that this does indeed hit the x-axis at kind of between negative 2 and 3 and between positive 2 and 3. I do actually want to take a look at the second graph where we said, well, we got plus or minus 3i. And what is of note here is essentially that we didn't get any real zeros. We only got imaginary zeros. So when I go graph this here, I'm going to change my window, and we'll go from negative 10 to 10 on the x-axis here, but I'll also, I guess I could hit graph here. It would be the same window. You notice that this never hits the x-axis, which totally supports algebraically the fact that we didn't get any real x-intercepts for this graph. And then for this last graph right here, if I were to actually look at negative 5 plus the square root of 11 and negative 5 minus the square root of 11, I'm actually going to look at this one in a Desmos viewing window. And we can see this here, and it's got a couple of zeros. Now the thing that I want to point out is this. If I were to actually say negative 5 plus the square root of 11, and I say, okay, let's do this. Let's copy this, and let's paste it and go back and change this to a negative here. Our two solutions that you see here are the x-intercepts that we actually do indeed get on our graph. So it is important to note that the x-intercepts of the graph are really the solutions to that quadratic equation. Cheers.